Okay, so hello and welcome again. So last time we derived the Blasius equation, and that is written here, the Blasius equation, right? Okay. So this is the Blasius equation. So I promised you that I will uh, clarify the solution method, that is the shooting technique for this Blasius equation, and I also promised you that I will code for you. So first I apologize that uh, I I cannot show you the code right now because I don't have that much of time, because I have to cover the things. Okay. Now, but I at the same time I promise you that I will show the codes very soon. But for that, for the time being, just let us see the philosophy of the shooting technique in detail. Okay, so we will solve this Blasius equation generally by shooting method. So this is a the so the Blasius equation is the solution for the physics of the boundary layer. Now just treat this as a mathematical equation. Okay, so as a mathematical equation, this is a like initial boundary value problem. Okay, so what we will do is a shooting method. So this comes totally under the realm of mathematics. So in shooting method, what we do is we break down this third order ODE into three first order ODEs. So the first step is break the third order ODE into three first order ODEs, right? So how can we do that? Let us assume f dash equal to some g. Then we have f double dash equal to g dash, and that we assume to be some new parameter, new variable h. So now this put this two equations, this and this, into this. Okay, then what we will get? We will get, here it is f triple dash, that means h dash. Okay, so because this means f triple dash equal to g double dash, and that is equal to h dash. So this will be h dash plus f into, and what is f double dash, that is g dash, and that is h. Okay, so that is h by 2 equal to 0. So now we have the required three equations, and those are this one, okay, this one, and this one. Okay, so these three equations we have, I can number it like 1 Roman 1, Roman 2, and Roman 3. Okay, so now I have to solve this numerically, no other way is there. So 2 is, so how can I solve this numerically? So if you have studied CFD, or you don't even have to study CFD for this. um, so as a mechanical engineer, if you are in your, at least in the second year of BTech, you must have studied the numerical methods. So there are some numerical techniques for the ODEs, right? Like Euler's method. Then we have the more accurate methods RK2 and RK4. Okay, so you can use any of them. So in MATLAB we have the conventional ODE solver that uses RK4. In Python also we have that. Okay, so for the time being I will show you, but just by a forward differentiation. Okay, so what we will do is we will divide our domain. So the domain was this, so this was the flat plate, right? And so the boundary layer was growing like this, so this is the coordinate eta. right? Okay, so this is eta, so this point is eta equal to 0, and what we do is we divide this domain into some points. Okay, so this is maybe I equal to 1. Okay, so this is I equal to 0. Okay, so this is I equal to 2, I equal to 3, 4, 5, 6, 7, and we can extend this up actually. So let me, okay, we can extend this up and we can take some 8, 9 and then 10. Okay, so we have divided our domain, and now we write this equation 1, okay, in a manner. So this is f dash at grid point, okay, I plus 1, no, sorry. So this is, I will write this equations at each grid point. So this is f dash at I equal to g of I. Okay, so then I can write this f dash I as f I plus 1 minus f I by, so let us assume that all these are equally spaced, and this spacing is given by some x or delta x. Okay, so this I write by delta x, and this is equal to g of I. Okay, then similarly I write the second equation, equation number 2, that is in the same form. So just replace f by g and g by h. So then it will become, I will write by another color. So the second equation is what, g dash I is equal to hi, right, and that will become again g I plus 1. Okay, I am writing directly, that will be equal to hi into delta x plus gi, right, and the similar in the similar fashion, f of I plus 1 will be what, g of I into del x plus f of I. Okay, and let me again write with another color. Okay, so another equation is h dash plus fh by 2. So this is h dash plus fh by 2 equal to 0, and that becomes, so at obviously at grid point I, all these things. So this will be h of I plus 1 minus h of I by delta x plus f at I into h at I by 2 equal to 0. Okay, so this will be hi plus 1 equal to what, hi, right, minus fi hi by 2 into delta x, right. Okay, now I have these three equations. Let me number these as 4, then 5, then 6. Okay, so now you see that put I equal to 1 here, I equal to 0 here. So then I will get what, f of 1 equal to g of 0 into delta x plus f of 0, and from this equation I will get, by putting I equal to 0, I will get what, I will get g of 1 equal to h of 0 delta x plus g of 0, and then from this equation putting I equal to 0, I will get h of 1 equal to h of 0 minus f of 0 h of 0 by 2 delta x. Now I will show you that why I am showing you all these things, because uh, in the code you are you will not be maybe using this Euler method, okay, but still I am showing you the algebra, because I want to know you, I want you to know this the solution method actually. So now you put what, I equal to 1, okay, I equal to 1, you put this. Similarly, then we will get f of 2 equal to g of 1 delta x plus f of 1, and here if you put I equal to 1, then you will get g of 1 j of 2 equal to h of 1 delta x plus g of 1, and here if you put again I equal to 1, then you will get h of 2 equal to h of 1 minus f of 1 h of 1 by 2 delta x. If there is any mistake in algebra, you please correct it, uh, but more important is to know about the solution philosophy. So then you see that if I increment this value of I by 2, 3, 4, 5, then I will get the values of the function g, h and f at all my grid points, right, from I equal to 1 to I equal to 10. But now to start the solution, you need to know the values of g0, f0, right, and h0, and then you can uh, then you can proceed. So for I equal to 0, for I equal to 0, uh, you need g0, h0, f0, that is the initial conditions for the each function. For I equal to 1, you need for the iteration I equal to 1, you need g1, h1 and f1. Then along that, for I equal to some k plus 1, you need gk, hk and fk. So at any iteration, to reach into the next step, next iteration, you need all these three values. So you cannot solve any one equation at first, then you say that yes, I will first get the values of g at all the grid points, then I will solve for h. That cannot be the case. Three variables have to be solved simultaneously, okay. So that was the first message, that the three variables have to be solved simultaneously, okay, three equations. So, and to start this engine of solution, we have to have g0, h0 and f0, those are the initial conditions, right. So let us see that if we have that or not. So what conditions we were having, okay, have I written the boundary conditions here? um, have I written that? Maybe not, or I don't remember if I have written that earlier or not, so let me write it now, okay. So at eta equal to 0, okay, so let me start by the actual physical variables. So now the initial conditions, or it is the same as the boundary condition for the problem, for the actual problem, okay. So then what we have? We have at y equal to 0 the no slip condition, that is u equal to 0. And if you have watched the previous video, then you will know that eta equal to y by some parameter, that means at y equal to 0 I have eta equal to 0, and u is what? So f dash, okay, that is f, small f, and that is equal to u by u infinity, and f was analogous to the stream function that I have shown, right, that I have shown here, that how f is analogous to the stream function, okay. So the derivative of f is analogous to u, so this will be f dash. So at eta equal to 0, f dash equal to 0, and I have my f dash equal to g, right, yes, f dash equal to g. So this boils down to at equal to 0, g equal to 0. Then what I am having at eta equal to 0, stream, so boundary is a streamline, okay, because no mass can cross the boundary, so boundary is a streamline. So at y equal to 0 I have my f equal to a constant, because along the streamline stream function is constant, right? Okay, so now I can take for reference this value as 0. You can take any other value, then you will get any other solution, okay, but generally boundary, by convention we take the stream function value as 0, okay. So and this boils down to eta equal to 0, at eta equal to 0 f equal to 0, okay. And we also have at y tending to infinity, that is at the far stream, okay. So at the far stream the velocity profile is a straight line, so it is not changing with y anymore, so the slope is 0, right? So this will be 0. So now you tell me that if y is analogous to eta, so y tending to infinity maps to eta tending to infinity, then and if u is analogous to f dash, then it is another derivative. So this will be what? F dash will tend to 0, and f dash is what? I mean f double dash, sorry, f double dash is what? F double dash is h. So this is so this means at eta tending to infinity, h of infinity should be 0, should tend to 0, okay, should tend to 0. So these three conditions we have. Which three conditions? So the first is h of 0 is what? H of 0. Okay, so we don't have h of 0. Okay, okay. So let us first digest that. G of 0 is 0 and f of 0 is also 0. So h of 0 we don't know. G of 0 is 0 and f of 0 is 0. H of 0 we don't know, but we have h of infinity that is equal to 0, right? But to start the engine I have told you that we need all these three, okay. So there comes the significance of the name of this method, that is shooting method. So now shoot for a value of h of 0. So here you shoot for a value of h of 0. So if you, let us say that you have assumed a value of 0.1, then now you can plug this value in this engine and then you can generate the solution at each of the grid points. So then you can find g, h and f at all grid points. So for a larger grid, I mean for a larger distance, so let us say at I equal to 10, at I equal to 10, you have to find h of 10. So if this is coming as 0, or it will not be coming as exactly 0, but if this is coming let us say at I mean point something, okay, it should come nearly as 0, okay. So that should be your check. So if this condition is satisfied, okay, that is h of this is tending to 0, okay, then your guess value or the shooting value was correct. If it is not tending to 0, then you have to shoot again. So by this method you have to find the numerical solution at each grid point, okay. So this was the philosophy of the shooting technique. Now there is a I mean additional point, that for the first two values you shoot arbitrarily, okay. So for the first two values you shoot arbitrarily, then you have, okay, so let me say that you have h of 1 0 as your first guess, h of 2 0 as your second guess, and then you get here h1 10 as something maybe 1, and then you get here as h1 of h2 of 10. So this superscripts are the iteration number. this has something 0.5. Okay, now you have to, then you have two values, and you know your target value is h10, that is equal to 0. Okay, so now you can interpolate, right? So now you can interpolate that what should be your next case. So next case is 3. Okay, so h3 of 0 minus, okay, h10, okay, by let us say h2 of 0 minus h1 of 0, then you can interpolate as what, h3 of 0 minus h1 of 0, sorry, h1 or h2, anything, you are just interpolating. So this will be what, uh, now for h3 of 0, what should be the value? This should be 0, right? This should be 0. So this is the value that we want. I mean here, so here is our, so LH is our guess or shooting values, and this should contain our target, right, that is h of 10. So this is the same concept. I mean, if you have to find some pressure, okay, so maybe this is the temperature and this is the pressure, so we know the pressures, but I mean we know the target pressure, but we don't know that at what temperature that pressure will arrive. Okay, so this is the same concept that you have applied when you are interpolating in your thermodynamic tables. So for the target we have what, here it should be 0, h3 is the achievement, I mean h3 is the desired guessed value for which h10 should be 0, and h1 of 0 was some value, let us say x, we had that as our guess, I mean sorry, this was the target, so sorry, extremely sorry. So for h10 we had our target value as 1, so this we have 1. Now for h20 we had our target value as 0.5. Again for h10 we had 1. Okay, so from this equation now onwards you will find your next guess values. Now if you put this h30 into your solution engine, then also you may come to know that your h10 is not coming as 0, but it will surely approach 0. Then you will again approach the same I mean interpolating method to go for h4. Now this will ensure that you will I mean you will converge much faster than if you were guessing arbitrarily. Okay, so this completes the shooting method. I promise you that I will show you the code. Okay, I will code you in I mean I will code this in front of you. Okay, so there you will get a better feel, and in the meantime you can try it by your own. That will be very interesting. Okay, so this completes the Blasius solution, or the I mean similarity solution for the boundary layer, thermal I mean hydrodynamic boundary layer. So now let us come to the, another solution of the boundary layer, that is called the integral solution. Okay, okay, so just let me give you a brief introduction that why we need this. So at the first we went for something called scaling or the order of magnitude analysis. So that was very powerful because we got the value of Cf as a function of the independent variables, that is x, re and another things L. Okay, so we got the form that I mean from the scaling analysis we got that delta by x will scale with 1 by Rex whole to the power half. Okay, so this was the scaling analysis, right? Then we have the exact value of delta, that is 5 by, you can check this. Okay, that is I mean this constant will come 5, okay, for the Blasius solution. So and now this becomes equal, not in the order of. So this is the Blasius solution or the similarity solution. Okay. Okay. So this is something what is very rough. Okay, this is very important because as an engineer, if you want to know that okay, if I increase the length of my plate, then what will happen? I mean, if I increase the distance x at a section A and at a section B, so if you want to examine that what will be the I mean delta or what will be the tau wall at B compared to A, then this analysis is there, this scaling analysis. You don't have to do this hectic Blasius solution. But I'm sorry. Okay. So this is a bit rough, right? What has happened? Sorry, just something. So there is a technical glitch that has happened. Okay. There is a technical glitch. So let me give me some time to solve this technical glitch and I will come back to you. Okay, so I apologize for the delay. So there was some technical glitch because of which I had to stop. So let us continue again. So what I was saying that this we got from scaling analysis, that is delta by x is of the order of 1 by Rex whole to the power half, and by Blasius solution we got the exact value of the constant, that is 5. So scaling analysis gives us a rough estimate and it does not give us the value of constant c, that is delta by x is equal to c into some Rex whole to the power minus half, and here we have that what is the exact value. Okay, so in between can I get some c approx, that is some approximated value of c. So this is the origin of the integral solution. So actually we don't need this delta, okay, and what we need is this tau wall or Cf or Cd or drag force. So this drag force or the tau wall shear stress, that is what we need. Okay, so I mean if without doing all of this you can design anything, then that is also acceptable. Okay, so engineering is the thing that if you don't obey the law of the physics, but if you can come up with a product that is meeting the needs of the human, then your product will be sold. Okay, so that is the beauty of engineering, but we have to obey the laws of nature, and uh, that is why we are doing all of the analysis. Okay, so we need, as engineers we need these parameters. So without the exact solution, if we can come to this to the values of these parameters, okay, within a marginal error range, then that is very good. So that is now our objective, okay, to get these within a minimal error range. Okay, so now here what we do is we approximate some velocity profile. Okay, we approximate some velocity profile. So the step is guess some velocity profile. okay, and then find these parameters. Okay, so now how can you guess the velocity profile, right? So I was having my plate here, okay, and the fluid was flowing over the plate, forming a boundary layer like this. Now I know the boundary condition here and boundary condition at the edge of the boundary layer. So let me draw a section here. So I know the boundary condition here at the plate and at the edge of the boundary layer. Okay, so my guideline will be, or the rule will be, the assumed profile, okay, the assumed profile should obey the boundary conditions and it should be obeying physics. That means that if you draw something like this, okay, so we know that the slope at the edge of the boundary layer is 0. So if you draw something like this, that at plate I know that the velocity is 0, so I put a 0 here and I do something like this and this, okay, that is the slope at here is 0. But can there be any circulation here? I mean, how can the backflow, I mean, there, I mean, I know that there cannot be any backflow and this type of abrupt velocity profile I cannot have. Okay, so you should obey this boundary condition, and you should also see that if my velocity profile is physical or not. You cannot have any arbitrary profile. Okay, so maybe you are having something like this. This is also not acceptable. Okay, so the shape of the, or the nature of the velocity profile, that from your experience you should judge that if I am going right or wrong. Okay, so that is the thing. And the more, I mean, the more the number of boundary condition that your assumed profile will be satisfying, the more it will be accurate. Okay, so now let us proceed. And to directly calculate the tau wall, okay, we have something like the von Karman momentum integral equation. Okay, so now let us study that. So the von Karman, okay, momentum integral equation. Okay, okay, so and here what we will be doing is just integrate the x momentum equation of the boundary layer theory with respect to y. So the x momentum equation is what? Okay, so let me write here, integrate x momentum equation with respect to y. Okay, so then so the x momentum equation is, so we are considering the flow over the flat plate. Okay, flow over the flat plate. So the x momentum equation says u into del u del x plus v into del v del y is equal to minus 1 by rho. Okay, so that, let me directly write this. So dp infinity dx plus nu into del u square del this thing. Okay, so then I am having this. So for the flat plate, we know that this thing boils down to 0. Okay, so what we can do is we can do the general formulation. I mean, retaining this dp infinity dx. If the plate is even not flat, then what you will do? So that will take some time, but let me do that. Okay, so here I will be integrating this whole equation with respect to y, 0 to delta within the boundary layer. Okay, then so I can write this del u del x as minus of del v del y, right, from the continuity. So this thing I have changed here. So these steps will demand a rigorous algebra analysis, and this is nothing but del del y of v square by 2. Okay, so I have made a mistake, that is this will be here. Okay, I'm sorry. So here it will be the same, I'm not changing this. So minus 1 by rho. Okay, now okay, so let us not change right now this dp dx. So this is dy plus I can integrate this. So this will be what? Nu into del u del y from 0 to delta. Okay, so let us work with each of these terms. So now let me work with this term. So I can do the integration by parts. So I can reduce the order of derivative del u del y by integration by integrating that. So this will be my first function and this will be my second function. Okay, so how I can write this? So integrating del u del y, that will be u, then into the second function minus u into derivative of the first function, this 0 to y, 0 to delta, and this will be 0 to delta. Okay, and this will be what? So this will be u v at delta minus u v at 0, and u v at 0. So at 0 both u and v are 0. U is 0 because of no slip, v is 0 because of no penetration. So this is equal to 0. Now what is this? So this will be u infinity, because u at delta is u infinity into v at delta. Okay, so how you can find this v of delta? So let us again go to the continuity equation. Okay, so the continuity equation says that del u del x is equal to minus del v del y. Integrate this equation similarly we have done with the momentum integral equation. Okay, then we have what, again del u del x with respect to y. So this we have now here, it will be v at delta minus v at delta plus v of 0, because we have a minus here. So this is 0 because of no penetration. Then we got the v of delta, right? So v of delta is minus of 0 to this del u del x. Okay. Now, so let me write all these things. Okay, u into del phi del y. So now see one more thing. Now let us come to the Leibniz rule of equation. I mean Leibniz rule of derivative under the integral sign. So it says that del t of alpha t beta t, and if we have a function of x and t, I am integrating. So this rule will say that if I can take the derivative out and in into the integral or not. Okay. Okay. So this is the Leibniz rule. Or Leibniz formula. So see that this formula is analogous to the Reynolds transport theorem. So this is the global derivative, and this is the integration of the local derivative. So this is the total change. Okay, so this is the total change, and this is the total change, and this is the change inside the CV, and this is the flux out minus flux in. Okay, so this is the same, I mean analogous to the RTT. This is the more general form of the RTT, you can say. Okay, mathematically more general form. So now here for this integral, if we apply the Leibniz rule, then what is happening? So for this integral, just see that beta is delta and alpha is 0. So alpha is a constant, it is neither a function of x then and neither a function of y. So this del alpha del t, that so here I don't have t but I have x, and instead of x I have y here in the integral. So del alpha del x equal to 0. Now delta is a function of x, obviously. With x the boundary layer thickness will change. But what we have as, okay, so let me write it. Okay, so del u del x dy 0 to delta, this is analogous to the this term. So this will be del x, and I can now write this as ddx. Okay, because after putting the limits it will be only the function of x. So this will be u dy, okay, minus, okay, so minus del beta, that is, okay, so these are the functions of x only. So d delta dx into u at delta comma y, right, u at delta comma y. Okay, because u is a function of x and y both, and instead of x I am putting delta, minus or plus. So because I have to put these terms into this side to get the value of this. So this will be plus, sorry, plus d of alpha is 0, d of 0 dx, and whatever this be, u of 0 comma y. So this is 0, right? This is directly 0. Okay, now what will be this? What is u of delta at y? U of is it making any sense? So this is what have I written the things. Okay, so here um, instead of x I am having y, and instead of t I am having x. So this is I have written, this is okay. Okay, so this is del d delta dx into f of beta comma x. So this is delta comma y. So this will be nothing but u infinity, right? Okay, so now let me proceed. So I have here u infinity into d delta dx, right? So just let me check it. I don't think this should be like this. Okay, so okay, let me proceed like this because it is coming like this. Okay, so this becomes what? This integral becomes, let me erase all this, and this integral becomes, okay, so I have written wrong here because u of delta comma y, this is not making any sense. Okay, this is delta comma x, at any x at u of delta, that will be u infinity. Okay, instead of y I have to replace this delta. Okay, now it is correct. These are some conceptual mistakes, you should always look for it. Don't just mug up that here it will be u infinity. You should always check that if it is really coming as u infinity or not. So now I am sure that it is coming as what? So del u del x, so it is coming as minus of what, d dx of this thing, and minus I can write this as, so u is, so u infinity is a constant, right? So u infinity, and delta is what? Delta is integral dy 0 to delta. So I can write this as this, right? Because integral 0 to delta dy is delta. So this is coming as, let me directly write it, d dx, okay, minus of d dx of integral 0 to delta u minus u infinity into dy, correct? Okay, now see that this whole term, okay, so this whole term boils down to this whole term, that is, sorry, so this whole term boils down to what? So this was v at delta. Okay, so this will be u infinity into this whole term, because I have found out this v of delta. So u infinity into this whole term minus this, so u infinity into u minus u infinity square, this of integral dy 0 to delta, right? d dx of this, okay, so okay, minus of d dx of this, so I have minus of d dx of this minus of u into u is inside the integration sign, so u into del v del y, right, this thing. Okay, so now see that this term here is same as this here is same as this term, right. So then I can write, now this whole equation boils down to this total equation, okay. So this will be minus 2 into u into del v del y dy 0 to delta, right. Then this term will come, sorry, then this term will come, that is minus of d dx of, okay, so let me absorb the minus, and this will be d dx of integration u infinity square minus u infinity into u dy 0 to delta, right. And here I will have what, so this term, okay, so this term will be, I have done it here, so let me check it once again. So outside the free stream, that will be p infinity plus half into rho into u infinity square, okay, so that is equal to 0. Outside the boundary layer for the free stream, Bernoulli equation is valid, okay. Now this will be dp infinity dx minus rho into u infinity into this, okay, right. So this is correct, okay. So then minus 1 by rho dp infinity dx equal to d u infinity dx into u infinity. So this will be what, this will be minus, sorry, this will be integral of u infinity into d u infinity dx into dy 0 to delta, correct, okay. So see, the mathematics is not important, I mean as an engineer the physical reflections or the, I mean what are the main essence of this, all these theories, those are important. This, I mean this von Karman momentum integral equation you can get by internet, okay. This derivation will come in your exam maybe, so in terms of that it is important, but what is more important is the concepts that are used in this derivation. So I am doing this algebra after a long time, so that is why I am being stuck at some steps, okay. So now this thing, so this is what, this thing is nu into du del u del y at delta minus del u del y at 0. So del u del y at delta is 0 because at the boundary layer and above that we don't have any what velocity gradient. So this boils down to minus of, right, minus of nu into del u del y at y equal to 0, okay. So now my objective is to put all the terms inside of a ddx. So this term has been casted in that form, okay, but now let me work with this term, okay. So again del v del y can be written as minus of del u del x, okay. So integral of this 0 to this minus 2, and that will be equal to minus and minus, that will be plus, so 2 into half into del x of u square into dy 0 to this, 2 and 2 will cancel out, okay. So now applying the same Leibniz rule, okay, applying the same Leibniz rule, so let me just put my brightness in a low mode or that will affect your visibility, so let me put it on, okay. I don't know, so let me put it on. So now applying the Leibniz rule, this will be ddx of, okay, ddx of u square du, okay, minus d delta dx into u square of delta comma x, and that is nothing but u infinity square, right? So that will be all over d dx of 0 to delta u square minus u infinity square into dy. Okay. So now this equation boils down to, let me complete this. So that means d dx of, okay, I am putting everything under one brackets, 0 to delta u square minus a infinity square plus a infinity square minus a infinity into u into dy, that is equal to, okay, so now for the flat plate, okay, du dx is 0, so this is 0 for flat plate, but I have shown that you can do the same thing keeping this, okay, so that will not affect anything, and you can actually see u infinity is not a function of y, and that is why du infinity dx, that can be a function of y actually, because I mean u infinity can be a function of both x and y, okay. So you can do the same analysis keeping the du infinity dx, but for the flat plate this is equal to 0, so that will boil down to minus this, okay. Okay, so now let me define what is called momentum thickness. So momentum thickness is 0 to delta u by u infinity into 1 minus u by u infinity into dy. So in fluid mechanics, in the boundary layer theory, you must have studied the displacement thickness and momentum thickness. I will not cover them in detail here because in heat transfer they don't bear that much significance. Okay, so displacement thickness is to compensate the mass deficit, and momentum thickness is to compensate the momentum deficit because of the existence of the flat plate. Okay, so I will not tell anything more than that because this is not a fluid mechanics course, and those things don't have to do much with this. Okay, so this will be equal to d dx of, okay, uh, so this a infinity will be cancelled out, and this will be, okay. So now if I divide by the a infinity square, so then you will see that it is this, right? This is minus of this, okay, and this is dy, so delta is equal to minus of, now this is what, mu by rho, this a infinity square, and mu into del u del y at y equal to 0 is tau wall, so that is tau wall by rho a infinity square, and minus will be cancelled out. So this is the von Karman momentum integral equation for the flat plate. So this is equal to d dx of theta. Okay. So in the next discussion, what we will do is we will assume some velocity profile u, then we will put it into this thing, and we will get some boundary layer thickness profile that will vary with x, okay, and we will compare that with the Blasius solution, okay, because ultimately we have to see that how accurate we are, and that will depend actually how you assume this profile u by a infinity, okay. So with that I would like to conclude today's discussion. If you have any doubt, any suggestion, you can put that into the comment box, and I apologize for the sudden breaks for the technical glitch, okay. So I promise that those things will not be repeated. Until that, goodbye and take care. Thank you.